All right, so what we're going to talk about today is we're going to focus on two equations. Actually, there are actually just one equation. And that equation is what we call the length equation or the mirrors equation. Equation is the same as a very simple equation. However, when you do this calculation, you have to be careful about the sign. So the sign convention is the most important part to get the correct answer for this application. Another thing I want you to know is to use the ray diagram. So in the lab, you're going to try the ray diagram. In the lecture, I'm going to show you some example of using the ray diagram. And afterwards, then you're going to do it by yourself. In the exam, you're going to likely to see some of the questions I'm going to ask you to draw a diagram. That's why once you finish the calculation, you also need to take a picture of your drawing and you have to submit a file afterwards. So these are the things we're going to talk about today. We also going to mention the lens maker's equation. That lens maker equation is how if you do like an eye exam and they're going to give you a prescription, and the prescription is actually related to the lens maker equation that we will talk about lens maker equation a little bit as well. There's another part of this chapter talking about the eye. I'm going to talk about the eye on Wednesday. On Friday, so Wednesday, we're going to do a bunch of example on Wednesday, and we will finish up this chapter. On Friday, we're going to review. I already posted a sample exam on Canvas, very similar to what we did before. You can use that as the way that you verify your understanding about this chapter. That's different from the practice one that I wanted you to do. The practice one is actually like extra credit added to your coming exam. The practice one is just for you to practice your understanding about this material. Question about this part? Okay, I need to change to my pad so I can write things on this note.
Question about the practice one.
What's that?
I had a question about the practice exam.
Okay, go ahead.
There's a part on there where we had to draw
A picture.
Yeah. So
yeah.
we use the that writing pad that's connected to the proctor exam, right? And then we upload that, we save it, and then upload it to the exam.
Yeah, or you can, if you wanted to draw it on paper, that's fine as well. Just take a picture of the paper. I just thought that would be easier that you use the one I just showed you, the one that like a notepad that
okay,
you can draw.
I tried drawing it on like my own paper and then snapping a picture, but the proctor exam wouldn't let me access like the email to get the picture.
Yeah, because it locked down. But I think I'm going to release that. So I don't want you to send like email, but if you cannot send an email, how can you? I will allow you to make a picture. And I think you could try in this way, like try this.
Have you reviewed any exams that were submitted yet?
I did. I haven't looked at yours.
I guess my only question was I just want to make sure that it was submitted correctly.
Okay, I will take a look and I will let you know, and I will contact you if I didn't see the file.
Okay, thank you.
All right. So so what happened is that if you take the exam, there's like a whiteboard like this one, and then you can. Did I say that? Yeah. And then you can actually make a drawing. Like if I wanted you to make the drawing and like a light that comes in, how the sync film is working, then you're going to show me how the light is refracted and then bounce back. And then I think you can save this, but I'm not sure how you can save this. There is a save function in the Zoom. If there's no way that you can save this, you can take a picture, then you can submit the picture as well. Okay, so you can also try to save the picture. I will take a look at the assistant and make sure that you have the way to submit the picture. While I'm investigating, I do need your feedback that when you take so for a lot of you haven't taken the practice exam, when you take the practice exam, I actually create one, the same thing that we did last time. I create another question, which is just right after the calculation. I want you to submit the file. So try to see if you can submit a file within the system. If not, then I have to fix something. So then you can submit the file. Any other question about this? Okay, let me go back to my pad. Okay, so these other things we're going to talk about. We already talked about plane mirror. We talk about the concave mirror. Any questions about those parts? I'm going to do a quick review about those things. Can you guys still hear me?
Yes.
Yes.
Okay, thank you. Because I changed to my pad. I have to turn off the other microphone, otherwise you're gonna hear an echo. So, all right. So we talk about the plane mirror, and we talk about the concave mirror. So let me just summarize these things first, and I'll show you some example in this one, and I'm gonna share my screen from my pad instead of the other one. We close share here and share my screen. Stop broadcasting. Okay, I believe everybody can see my pad right now. Okay, this is nothing to do, you guys. This is another class. Change to 121 geographic. Okay. All right, so this is the one that we're going to talk about. First thing about the mirror and the difference between the mirror and the lens is the mirror, one side is opaque, so light cannot penetrate. Because light cannot penetrate, you can see the image was because of the light of the refraction. So over here, you can see, I say the mirror is based on the refraction. It's based on the light refraction. When we talk about the lens, you're gonna see the image was based on the refraction, meaning the light actually turn to a certain angle, and that turns certain angle is what we call the refraction with the R. So plane mirror, concave mirror, and convex mirror, they are all the same. They have one side which is opaque, light cannot penetrate, so light will bounce back and with the refraction, and that's where we're going to find the location of the object. Our brain, our eye and brain do something else. And that something else is we, in our brain, is going to interpret the image. Sometimes it's going to be on the back of the mirror, and that is what we call the virtual image. If you can actually phone an image from a film, and that's the image, what we call the real image. So in a lab, you're going to see what the difference of these two. Doesn't matter what kind of image that you have, real or virtual, we can always see it. We can see the real image. We can also see the virtual image. Most of the time when you look at the mirror, well, actually all the time when you look at the mirror, you're looking at it yourself. That image is what we call the virtual image. It's not the real. It's not the real image. It's a virtual image, but you can see it because you can see yourself standing inside of the mirror on the back of the mirror, which is not possible, but that is the image you see. The reason we can see it was because our brain is going to interpret that light is actually coming from the back of the mirror. Even though it's not possible, but that's how our brain will interpret that. So that's why we call it a virtual image. The prime mirror has some property that the one of the property is that we know the distance of the object and the distance of the image is going to be the same. So over here, we write one equation, the DO equal to the DI. Now, I wanted to put some cautious about the sign over here. If the DO and DI, you all represent that in terms of the number, then it's going to say the number is going to be the same. But if instead you put a sign of that, which is the meaning like this. So I have a plane mirror over here. This is my plane mirror. The plane mirror has one side which is opaque. And I have my object over here. I'm going to see my image on the other side of this mirror. So this is going to be the image of your object. The way we define a DO is the distance of the object. This is the DO. And the DI is going to be the distance of the image away from the mirror, okay? It's away from the mirror. You look at, same thing for the lens. When you find a distance, it's the distance from the object or the image to the mirror or to the lens. Now, the sign is this way. If the sign of the object is at the same side of the object, if the, so we define this side is positive. The object toward to the object is the opposite, is the positive. And this side is going to be negative. If you represent the D as in like a location of this axis, then DO simply is a positive number, and I is going to be negative number. Then we will represent the DO equal to negative of DI. That simply meaning if you wanted to use an axis to represent that, then you use this way. But anyway, you know that value should be the same. Another thing we know about this is that if we mark the height of the object and the image, then their height is also going to be the same. Okay, so we say the front of the mirror is positive and back of the mirror is negative. And what kind of image this is? Well, we already told you if you have a pair mirror, it's going to be a virtual image. How do you tell an image is virtual or real? Well, the two kind of way you can identify. One is the light is actually not coming from that place. The light is not coming from the image. That is going to be a virtual image. Because it's on the back of the mirror, it's not possible that you have any of the lights coming from the back of the mirror. The second way that you can see is you look at the orientation. If the orientation is the same as the orientation of the object, then we call this the upright, and that is going to be virtual. So whenever you see the upright, it's a virtual. So when you see other people, you actually see a virtual image. That's weird, but that is what we call a virtual image. Okay, now, can we form both the real or virtual image if we use different kind of mirror? Well, we kind of show you, if you have a concave mirror, then you can actually form both the real and virtual image. And we tell you the rule that you can draw a virtual image or the real image from a concave mirror. So what are the rules? There's like 3 different rules. So the first rule that you write is that the rays, the parallel to the principal So what is concave mirror? Well, concave mirror is this one here. This is the concave mirror. And we defined several points already, so you should be familiar with those points. One is the focal point, one is the C, which is the radius of the circle. In the book, they use R, so if you see the book use R, the R is our C. So the rays that's parallel to a principal axis will refract from the mirror and pass through F. That's the first line you draw. The second line you can draw is the rays they pass through the C. It will pass through the C. So it's just coming back and forth. You only need 2 rules. You only actually need 2 rays to find the solution. When there is an intersection, then that is where the image is going to be. But the third rule is very similar to the first rule. The third rule is to say, if you have the rays that pass through, the F, and it will refract by the mirror, and it's going to be parallel to the principal axis. Oh, not pass through, let's be parallel. Okay, so very simple rule, and let's just do one example over here. Kind of review, we did this already, but let's just do this one in a very quick way. So first thing I do is let me just draw a simple line at here. So a simple line represent the principal axis.
Lost you for a minute.
What?
Your voice was cutting off. I don't know if it's with everybody else or it's me.
Really? It happened before. I'm not sure why.
So, Professor, is it possible you can all these 3 diagram rules? You can do it with the diagram. Can you show it with the diagram?
What diagram are you talking about?
Like the ray diagram, like you said, rays pass through F will reflect from mirror and parallel. So can you like try it and show it?
I'm going to show you an example over here right now.
Okay, sorry, thank you.
Yeah. Wow. Man. Okay, so here I have a line. And let me draw a curve which represent my mirror. This is the mirror. This is a concave. It has a point called the F. it also have a point called the C. One important thing that we can say is this F is approximately equal to C over 2. Okay, remember this. The focal point is approximately equal to the radius of the mirror divided by 2. Same thing for the lens. When we go to the lens, you will see there's also a focal point as well. So these are the 2 points that we have. We can put our object in front of this concave mirror. So let me put the object in this way. If I put my object at here, I think we did this before, but let me just use this one to show you how we drew, how we make the ray diagram. In the lab, we're going to do a ray diagram as well. So if I put object over here, then I've used the 3 different rules to find the light rays. First one I'm going to draw is based on the rule number 1. So let me use the rule number 1. The light parallel to the principal axis will refract and it will pass through the F. So refract, pass through the F. F is here. That's rule number 1. Rule number 2, the ray that pass through the C will refract from the mirror. So the light ray of this one here is going to be the light coming pass through the C. This one here, it will bounce back. Now, if you look at these 2 lines on the left-hand side, on the object side, and they are going to diverge. There's no way they will intercept in that direction on the left-hand side. The only way they can intercept is on the back of the mirror. So you are going to extend this such that you can actually make it into an interception. So if you continue to extend the blue one with the red one, you're going to see they intercept at a certain point. And that point is the point where your image is located. Which means if you actually draw the object, this object is going to be like this. Okay, so any question about this part?
No.
Okay, what about the third line? Can you draw a third line based on the rule? Let me just draw the third line to you. So this is our concave mirror. The third line, let me use a different color to represent. Let's use the green color to represent it. Well, the third line meaning that if you have a light, well, that is pass through the F. So light coming from the tip and go through the F is this line here. And it will bounce to the mirror and it will parallel once it pass through. So ideally this one will go this way. So if you have a light that pass through, it's supposed to bounce back, it's supposed to parallel to your principal axis. But on the back of the mirror, you can see a dashed line like this, and they will all intersect at the same point. That's where you find the location of the image. Okay. Now over here, let me define several things over here. The F, this F is the location from this place to this place. From where your mirror is to the point where all the light will concentrate at that point if you use the parallel line. So if you have the parallel line coming from the left, all the light will concentrate at that point. That point is what we call the focal point. So that's the focal point. Now, the radius, which is the C, is the point from this location to the mirror's equation, the mirror's location. So this is the C. We also have a location of the object. So the location of the object is the location from the object to the mirror. So this is your location of the DO. And you can also find the location of the image, which will be on the back of this one here. This is represented as the DI. Another two variable we can define is the height. The reason we care about the height is sometimes the image will be larger, sometimes the image will be smaller. We want to find out would that be larger or smaller, and that is what we call the magnification. So if I make the height of this, and this will be the height of the image, this one here is the height of the object. Okay, so these are the several, like the way we look at the image. So make sure that you understand how you use the rules to draw the ray diagram, and how do you define those locations, because in the lab you're going to measure those locations. Okay, I'm going to show you some setup that you had to find out the location of the of this one. Now, if we wanted to calculate, we can actually find an equation to calculate the location of those objects, and that equation is what we call the mirror equation. So the mirror equation is similar to the lens equation. That equation, let me just write it down over here. The mirror equation is this. The DO represent the object distance. The DI represent the image distance. The F represent the focal point distance, the focal point position, and the C represent the radius of the curvature location. And we told you the F is approximately equal to C over 2. Wait.
The inverse.
Yeah, it should be 2 over C, right? So this will be 2 over C over here. So once you want to find the location, you can use this equation to find the location. Now there's certain rules to tell you what sign convention that you should use. We told you if the object is in front of the mirror, which is on the left-hand side, and that will be a positive. So you want to use positive, this is on the left-hand side. So let me write down some of the rule over here to determine how the location should be. Okay, the first thing we look at is the F here. Try to see where my nose is. Got this. Be very careful about how you write the location, otherwise you're going to get the wrong answer. Use my nose. Can't find it. Oh, here, got it. The sign for the focal point of the C, the curvature, is this. For this kind of a mirror, they are positive. If you have another kind of mirror, this is what we call the convex mirror, and they are negative. So for concave, the F value will be positive because it's on the left-hand side, is on the same side of the object. So it's in front of the mirror, then will be positive. For the convex, that you can see the convex, your focal point is going to be on the back of the mirror, so that's going to be a negative. So this is the focal point of that kind of a mirror, and we put a negative for that. So this is the sign for the F. Another sign that is important for the equation is the DO. DO is going to be positive because it's in front of the mirror. Now the DI could have a positive or negative. If that is the positive, meaning it's in front of the mirror. If your DI is negative, that means it's in the back. Okay, any question about these value?
You have a question in the chat, Professor.
Thank you. Okay, so someone is asking you how to find a focal point. How do you find a focal point? Well, focal point, so during the lab, you're going to do this actually. So if I put a light source, I put an object, then I start to get a lens or the mirror. I change the location such that I can see an image. Then I can use this equation to find the F. Normally, we use a setup to measure where the F is. Once you know the F, then you can predict where the image will be. There's also going to be an equation, which is the lens maker equation, that can help you to find that as well. By knowing the geometry of the lens and also the index of refraction of the lens, you can also find the F. But over here, let's just say F is just a number. So in this equation that you see, the A equation, if you know two of the value, you can find out the other one. If you know where you put the object and you know the F, then you can know where the image is. If you know where you put the object, you know where the image is, then you can find out what is the F, what is the focal point. Same thing for the C. Okay, so you can use that and, to find out what the location of the F is. Okay, so these are the convention, the sign convention you have to pay attention to. Now, one thing I wanted to point out here is, what about the image? If you, so the image depends on, you could have a positive and negative. If you have a positive, it's going to be in front of the mirror. If you have a negative, it's going to be on the back of the mirror. And we said there's an image of the real image, there's a virtual image. Which one is the virtual and which one is the real? Well, again, if the image is that you see is on the back of the mirror, that means a virtual. So this one is going to be a virtual. And this one is going to be real. If that image is in front of the mirror, you're going to see it's going to be real. If the image that you see is on the back of the mirror, it's going to be a virtual. Now, what is the real image orientation is? The real is inverted. And the virtual is upright. Okay? So, image on the same side of the object is inverted, is real. Image is on the back of the mirror, is virtual, is upright. Another equation related to the mirror's equation is this. You can also find out what is the magnification. The magnification is something to do with the ratio of the high. And the ratio of the high is the height of the image to the height of the object. If the image is larger than the object, you are enlarge the object, right? The lens or the mirror is going to enlarge the object into an image, and vice versa. Now, this one equal to this. This one equal to minus di over do. Pay attention to the sign over here, the minus over here. Well, magnification feels like just a number. If the number is larger, meaning an image will be larger. If the number is smaller, the image is smaller. So if it equal to 1, meaning it's the same size. The minus sign over here tells you the orientation. If you got the magnification that is negative value, that means your height is actually upside down to the object, which means if you have an image like this, if this is the image of the height, you're going to put a negative value over there. And that simply just tells you, you know, that image is going to be a real image. So this negative sign over here represents whether you are going to have a real or a virtual, or whether your image is upright or is inverted. So if you have a negative, that means you're going to have a real image, because a real image is inverted. If you got a positive M, it's going to be a virtual image. Okay, so any question about this part over here? About the height, HI, the height of the image, if it's a positive or it's a negative, what does that tell you about the image? If it's a negative, it's a real. If it's positive, that is a virtual. Positive meaning is upright. So this one here that I just show you, this is an inverted. Then if you got this height like this, then this is what we call the real image. The blue one is the upright, that's positive H, so that is going to be a virtual image. Okay, let's do an example over here. So the example that we show you is an object is 1.5 centimeter tall, it's placed in front of the concave mirror, it has a C is 20.0 centimeter, want to find the image distance and the height of the image, and use the ray diagram to show the location and orientation of the image. Okay, so if you are having this question in the exam, so what you have to do first, and then you probably can use the image, the mirror's diagram directly, use the mirror's equation directly, and to find out what is the location of that. Then you can draw the ray diagram to show what that looks like, to verify kind of your result. So key things to identify several things. 1.5 centimeter is the tall. The object is located at a certain place. It doesn't tell you, but it tells you the mirror that you have has a 20 centimeter of a C. Now, it's important also to know what kind of mirror that you have. Well, you have a mirror which is a concave mirror. The concave mirror is going to tell you the orientation of where the F is located. Now, from this, we want to find the image distance. So what is the image distance? And what is the height of the image? Well, let's just write down all this parameter that we try to find. 1 centimeter is the object height. So this is the object height. And it's tall, so it's go upright, so the positive value is 1.5. That's the positive value of this. And the concave mirror, okay, so you also got a C equal to 20 centimeter. And we just said, if you have a concave, which is this one, the value should be positive. So this is a C, which is positive. We want to find this one here, DI. And we want to say, we want to find out what is the height of the image, which is the H of I. Okay, so how do we find the solution of this? Can we use the equation directly to find?
Can we use the mirror equation to find DI? And then from the mirror equation, we can use the lateral magnification equation to find HI?
Yes, we could, but the first thing I haven't give you is we are still missing one thing, and is where the object is. So to do this calculation, another thing you need to know is where the location of the object is. So let's say the object is 14.0 centimeter in front of the mirror. And you look at the equation, so the 14.0, this is your DO. This is a DO. And DO is positive. This is the object, the location is always in front of the mirror. So in front of the mirror is going to be a positive. So we use the length equation, the mirror's equation, 1 over DO plus 1 over DI equal to 1 over F, or equal to 2 over C. We don't know the F, but we got the C, and we know the C is 20.0 centimeter. And we got the DO, which is a 14.0 centimeter. Then we can find out what is the DI. So you simply put these values, then you can find out the DI. So let's just move on to the top, and then let's solve this one over here. So you got 1 over 14 plus 1 over DI equal to 2 over 20. So your 1 over DI is equal to 2 over 20 minus 1 over 14. And that will give you a value. And if you do this calculation, the value will be equal to 0.0286 centimeter, 1 over centimeter actually, because the bottom is in centimeters, so you have the value over that, that would be inverse of the centimeter. Now, what we want to find is DI. So the DI is actually 1 over 0.0286 centimeter inverse 1. And that gives you the distance of the image. And that distance is 35 centimeters. Okay, so that simply tells you the distance of the image is 35 centimeters. Now, the second thing we want to find out is the orientation. We want to find the height of the image. So what is the height of the image? The height of the image you can base it on this N. This is a lateral magnification. That is equal to height of the image over height of the object. This is also equal to negative of DI over DO. What is the value? What is the sign of the DI? Well, we just solved the DI as a positive value. So you're going to put the positive value in there, but there's a negative sign in front of that. So this is negative 35 centimeter. What is the object height? Well, the object distance. The object distance is 14.0 centimeter. and object is in front of the mirror, so it's going to be positive value. So that tells you the ratio, that actually tells you what the magnification is. So this magnification is actually equal to minus 2.5. And what do we tell you about the negative means? Okay, over here, negative meaning the image is real. If the image is real, that means it's inverted. That means the image is upside down. And that means your high should be a negative value as well. All right. So what is the high? Well, the high is equal to negative 2.5 multiplied with the object height, where the object height is 1.5 centimeter. That will give you negative 3.75 centimeter. Okay, question about this part. Now I'm gonna skip the part that we have to make a drawing. So if you know this idea, then you can use the same way, the different rule to find a location, and just using the ray diagram to show that. In the lab, you're gonna do similar things. So let's just use a very quick breakout room to let you do this one here. Just wanted to make sure.
Dr. Chow, I have a quick question. So, I mean, I know how to draw the diagram, like if we had to use a ray diagram, but like sometimes when I make mine, my lines won't match like the ways yours do. So do you have like, I guess like any like tips on how to make sure like you're drawing all your lines correctly?
I think the way, because you couldn't make the line up or intersect at the same point, was because the curvature. There's no way that we can make such a precise, like a drawing for the lens, for the mirror that you're using. So
Oh, okay.
you cannot make it line up was because of that. But you can kind of estimate. I mean, I'm not going to ask you to draw like precisely, but you can at least show it's going to be a larger or smaller, or it's going to be intercept at the front or on the back of the mirror.
Okay. As long as we get like which side and like if it's bigger or smaller, it doesn't have to be like the exact.
I would say, for this kind of case, I would say the best way to draw this is actually just show two lines first. And so the first two line I would do normally is the first line and second line. The second line is that you find the center of the mirror. And once you decide the location of the C, the F is the half of that distance. It would be the middle between the C and the mirror that you have.
Okay, thank you.
Yeah, and then you draw the line, go through the F, or draw the line, go through the C, and also the line coming parallel and go through the F, which is this line here and this line here. So two line is good enough to find a location. Okay. All right. So have we tried the breakout room before? We did, right? We did this for the lab. So let's try this one for the lab. And no, not to the lab yet. But I want to just spend like 10 minutes, work on this problem, and you try to draw the line. I'm going to randomly assign people to different groups. And you guys can discuss with each other. The problem you are going to solve is the same kind of a setup, then the same kind of a mirror, but you're going to put the object is 6 centimeter in front of the concave mirror.
So it's going to be 6 divided by 2 equals to 3?
No, 6 is the object.
Okay.
Okay, you guys okay? Now I'm going to open the rooms.
Yes.
Hello? Hey, you have question? Okay, are you guys come back? Have you guys come back?
Yes.
Yeah.
Yes.
Yes.
Okay. Sorry, I just all right, so if you do it correctly, your diagram will be look like this. The focal point is 10, C is 20, so F is 10. Your object is 6, which is actually in front of the F. So your image should be somewhere on the back of the mirror. If you make the diagram, it will be very similar like this. This distance will be longer than the distance of the object. I believe the answer for that is -15, which is the DI. Equation that you use is this equation over here. That's 1/6 plus 1 of DI equal to 1/10. And you move this one to the right hand side. That's will be 1/10 minus 1/6. And that will be equal to 1/DI. Then you can find out the DI. 1/10 is smaller than 1/6, so 1/10 minus 1/6 will be a negative value. And that's why the value that you solve will be -15. Once you find that, you can also put it into this equation over here to find a magnification. You'll be able to find the height of the image. You can find the height of the image and simply just multiply that with the m. So m times the HO, the object height, 1.5 centimeter, you can find the image height. Okay, for the height of the image to be positive or negative value. The DI is negative value, so you put a DI negative value with another negative sign, it gives you the magnification, which is positive, meaning the object is, the image is upright. The image upright is a virtual image, so H is also a positive value. It's on the back of the mirror, so it's a virtual, it's upright. So everything should be able to confirm your calculation. Question about this part? I do this one slower because once you understand this, then the rest of the thing is going to be similar to this. So after this, then I will start to look at the rest of the kind of situation in a very quick fashion. So I'm going to start to talk about I'm going to use another one, so that's why I changed my screen. Sorry about that. I'm just being a little bit way to share my screen here. So any question about that concave case? Okay, now if you don't have any question about the concave case, then let's do the convex real quick. It's the same way that you do the ray diagram, and the rule is about the same. You only need like two. So one is going to be the one that you do the parallel, and the other one is going to be you have another ray that goes through the center. So if you do that too, then you can also find the location of the object. So the rules for that is this. So the first rule is that raise the parallel to the principal axis will refract and its extension will pass through the F. The reason why we said the extension is this. So your concave mirror is like this, or the convex mirror. This is a convex mirror. The F is on the back of the mirror, so this is in the F point. So if you have the light coming from the object, this is an object, light parallel to this one here, then it will reflect. So it will refract. It will come back to where it's coming from. But we make the extension of this reflected light, and this one will penetrate this F. So it will pass through the F. So the light actually reflects back. Will extended of that will pass through the F. So how do you find out where it reflect back? Is that you make the light from the mirror to the F point. So that's the first light I was drawing over there. The second rule is that you make the ray go through the object to the C. And the light that goes through the C will go back and forth, so it's going to be a straight line. So if I draw the second line, which I use a red color, is so where is the C? Well, the C is here. So where is the object? The object is right here. So you connect the object and also the C. So this is a line that you draw. This is the second line that you draw. So from the object to the C is going to be a straight line, and that will give you what the image looks like. So the interception point is that here, this is where your object is. Therefore, if you draw the picture of that, the object is going to be like this. So what does that tell you about the image? The image is always going to be a virtual image because it's on the back of the mirror. And what about the size of that? In this case, the size is smaller because it's shorter. So that's how you use this one to find the location of that. Any question about this? Now, you can also use the equation, the same equation that we showed you before. When you have a convex, this is a convex mirror. The same equation, dO plus 1 over di equal to 1 over f. This is negative because it's on the back. It's not on the same side of the object. This is going to be positive. The object is always positive. It doesn't make any sense if you put the object on the back of the mirror. It's not going to give you anything. So this dO is always positive. The di, if you do this calculation, what is the di? Well, the di is always going to be virtual, meaning it's always going to be on the back of the mirror. So this one is always going to be negative. Okay, so that's what this is. This equation is going to be. Any question about this part? Okay, there is one example. I don't have time to go through this one example, but you can try this. So when you do this convex mirror, and just quickly just write down all the information that you have. Over here, you got the object location. This is dO, which is a positive 14. Tell you the image is 5.8 behind the mirror. So this is a di. This is negative 5.8 centimeter. And the focal length, we want to find what is the focal length. So how do you find the focal length? That's how you find focal length. And you're going to find out the f is going to be of negative value. Okay, because 1 over 5.8 is larger larger than the 1.14. So this result on the left-hand side is going to be a negative value, and then you take 1 over that value is going to be the f of your answer. Okay, question about the convex. Okay, now next topic that we wanted to talk about is the lens. So the lens, as I said, lens is that the light will penetrate, light will transparent the lens, and when you transparent, when you penetrate the lens, it will start to bend because the index of refraction is different. The lens, the glass or the plastic, they has a higher index of refraction as opposed to the air. So light coming from the air penetrate a lens and it's going to start to bend. It depends on how it bends and depends on the shape of the mirror, the lens. We have two kinds of lens. One kind of lens is called a convergent lens and the other one is the divergent lens. The shape of the lens like this. So if you're looking at the convergent lens is this. The divergent lens is like this. If you have a convergent lens, if you think about the light, so the light, if they're going horizontally, when it goes to a lens, it will bend, right? So how would it bend? Well, if you look at the shape of this curve over here, this is probably is the curve of the shape right at the point that you hit on that lens. And if you make a line, which is the vertical line along this one here, this is a line perpendicular to that intercepting point of the light ray and the lens. The angle of the incoming light is this. What is the angle of the refracted light, which is a light that goes into a lens? The light pass through this is going to bend even more, which means it's bent even closer to the screen line here. So it's going to bend toward to the center of this lens. When it goes to the air, then you're going to look at the other surface of this one here, which is going to be somewhere around here. Now this is going to be another line, and you do the similar thing. So without going into the detail of this, you're going to see the line actually going to be like this. So if you have another line coming from the left, from the bottom, and this one going to bend and it's going to go this way. Now, if you use all this parallel line and they all pass through this lens, and somehow they will also concentrate at the same point, that point is what we call the focal point of this lens. Now the lens is different from the mirror. The lens, you can have the light coming from all directions. You can have the light coming from the left-hand side. You can also have the light coming from the right-hand side. So when we write the focal point, you actually have two focal points, depends on which side you're looking at. When you look on the right-hand side, which you're actually looking at, this shape of the lens, this curve over here give you the focal point on the right-hand side. You look at the other side, which is the black one here, you're going to get another focal point if the light coming from the right-hand side. So that is the focal point corresponding to the right-hand side of this lens. Okay, question about this part. Let me give you the rules. So when you do the lab, you know how to find the image location. So how do we find the image location of this kind of lens based on the ray diagram? So the first rule is, if you have the ray that is parallel, again, it will pass through the lens. It's not refract, it's pass through. And it will refract, meaning it will bend. And it will pass through and it will pass through the F on the other side. It actually is the focal point of the red one. So if the light comes from the left-hand side, which you're looking at the lens of the left-hand side, it will pass through the focal point of the left-hand side, which is on the back of that lens. So this is the first rule that you're going to use. The second rule is this. The second rule is actually very simple. You look at the rays that pass through the center of the lens. If that light is passed through the center of the lens, it will go straight. So where is the center of the lens? This is my lens. The halfway of this one is the center of the lens. This is the center of the lens. If you put an object and then you plot a line pass through the center of the lens, for example, if my object is the object here, let's say this is my object. And the line that you're going to draw for the second one is this line over here. This is the line that coming from the object will go through the center of the lens. It will continue go straight. So this is the line based on the rule number 2. Rule number 1 tells you if you have a line that goes to parallel, and it will pass through the lens and it will bend to the focal point. So if I draw that, oops. This is the number 1, the black one. Go here and it will bend. It will bend through the F. Okay, so that's the 2 line that you need. You are going to see that if you continue to extend this, this is actually, well, sorry. This is actually going to intercept on the right-hand side. So if you continue to extend this, at a certain point, they're going to intercept. It's not going to intercept on the left-hand side because on the left-hand side, they're going to diverge. But on the right-hand side, they're going to converge into a point. And when you have that point, is the location of the image. Okay, any question about this part? You can also write the third rule. Actually, if you wanted to write the third rule, there's another light ray. This light ray is this. If you have the rays that pass through the focal point on the object side, and when it goes through the lens, it will parallel the optical axis is actually the principal axis, but let me just write the principal axis. So that just simply said, if you have another line which is come the object side, which is this one here. So if I make another color, this one here. So a line that pass through this one here, you can see I'm running out of space. It will bend, which is a parallel to the principal axis. So if you draw this correctly, you're supposed to find a location which is somewhere around here. Again, it depends on how perfect that your curvature that you draw on this lens, then your location might be a little bit off, but I don't really ask you to write like a very perfect drawing, but as long as you can show the idea, at least you know the orientation, you know that's a real image or a virtual image. If it's on the upside down, it's going to be a real image. So what this tells you is that you're going to see a real image, right? The real image is going to be on the other side. Okay, any question about this part? I have a question in the chat room. Zoom out like this. Okay, question about this? We're talking about converging lens. Now, there is also a divergent lens. Divergent lens, you also use the same idea. You only need like two rays. You can use the first and the second. Follow above rules, then you find the location of the image. Let me just make like an example over here. So if I make a center line here, this is my principal axis. This is the line to help me to find where the center of my lens is. So this is the center of the lens. For this kind of a mirror, you also have a focal point of 2. So one focal point is going to be at this location. That focal point is represent to the focal point of this side over here. It's different from the above one, the convergent lens. You also have another focal point on the other side, which is this one here. So this is an F, and this is also an F. They were corresponding to different side of the lens. You put an object in front of this. So let me just put an object over here, then put an object at here. This is my object. I want to find the location of my image. The first line you draw is going to be the line that will be like a parallel to this one here. When this line goes into this divergent lens, what happens is the line will bend outwards. It will bend in this direction. It will be refracted, it will be bended to something away from the center. But if you make the extension of that, it will pass through the focal point. So the way that you find the line is that you look at this way to find where the line extended to. Because if you look on the right-hand side, because they all diverge, that's not possible that you find an image on the right-hand side. The image has to be on the left-hand side. The second line you draw is the one that goes through the center. So that's the simplest one that I like about this. So the line is always going through the center. It will go straight, and that's the line that you draw for the second one. Now you can find an intersection point. That is going to be the intersection point at here. So this is where the image looks like. You can see in this case, the image is going to be upright, which is a virtual image. Upright is a virtual, and it's going to be a smaller version of this object. All right, any question about this part? Okay, so we have kind of finished all this drawing, the ray diagram, and give you the rule how you can make the drawing. There is also an issue about how the sign convention should be. This part is kind of a crucial as well. So let me just write down like a few things about these. So the sign convention for the length equation. The length equation is the same as the mirror equation. That's very simple, right? This is a very simple equation. Second equation. Let's start with the F. If you have an F, then it's going to be negative for divergent. If you have a divergent length, F will be negative. What is divergent? Divergent is this kind of shape. It's going to be positive for conversion. Conversion is this. That's F. So make sure that if you got some like a statement about a problem, they tell you what kind of length that is, then they given you the F, then you have to know which one is positive, which is negative. Or when you solve a problem, they didn't tell you what kind of length that is, but if you put the value in there and then they give you the positive, negative, then you know which kind of length that you're using. DI is going to be positive if it's on the opposite side of the object. Meaning object on the right and the image will be on the left, object in the left, then the image will be on the right. Well, the vice of this one is that if it's negative, then it will be the same side of the object. So if that is the case, then you can also tell what kind of image that is. If they are in the opposite side, the image will be inverted. So this one will always tell you this is going to be a real image. It's inverted. If this is on the same side, this is going to be a virtual. And it's going to be upright. It was the one that will just show you of this one here, right? This one here is it's going to be a virtual, it's going to be upright. So that's the F and the DI. Well, if you look at the H of I, if H of I is positive, then it's upright. When it's upright, that means it's virtual. If it's a negative, meaning it's inverted, and this is going to be real. If your HI is positive, then the N is also positive. Because the N is HI over HO. And the N is negative, then it's going to be a real, it's going to be inverted. So these are the sign convention for the length equation. Okay, any question about this? Okay, I'm going to give you guys a couple minutes to write this down. Can we just take a break for like 10 minutes? You guys
That
okay?
is perfectly fine.
So let's take a 10 minutes break and then let's get back at the 45, a quarter before 3. And then I will continue do the lab.
Chao, will you also be posting these notes online on Canvas?
Yeah, I will.
Okay.
So in the meantime, let me print this to a PDF so you guys can download and take a look.
All right, thank you.
All right. So
Thank you, Chao.
Okay, we'll be back at 2:45.
Okay, thank you.